before talking about entropy, well, you've seen entropy before. This was in a way the objective function for multilinear logistic regression. Multinomial logistic regression. And the formula for the entropy was negative summation of pi log of pi. Okay, that was the formula for the entropy. We didn't exactly use this one. We had, for the multinomial logistic regression, we had delta ij log pij. But the delta ij are the number of occurrences of something, and if you divide that by the entire population n, that becomes probability. So it's basically the same thing. But I want to first talk about this log pi with the minus sign. Let's say you have a data set with 8 elements. I want something fun. Let's say these are Pokemons. What kind of attributes does Pokemons have?
Type, attack, special attack.
Okay.
I was just saying color.
Okay, so let's say
Color.
Shiny, unshiny.
okay, let's say shiny, unshiny. Shiny, unshiny. Okay. And then these have special attacks. These don't. No special. Special. No special. Okay, what else do you have?
Speed.
Huh?
Speed.
Speed?
High
Like-
speed or low speed.
Okay, high speed, low speed. So let's say the ones that we have, like squares in here, are high speed. So this means high speed. And let's say these are a deck of Pokemon cards that you have, all right? And you shuffle them, you pick one, right? And we want to talk about the probability versus information content. So think about probability versus information content. Suppose you got this one guy, right? What's the probability of selecting this one? It's shiny and it has a special tag and it's high speed. Probably the best one in this card, right? Okay. So what's the probability of getting this one? 1 out of 8, 1/8, right? So this one has the probability. So getting a shiny with special tag and high speed is going to give you 1/8 probability, right? So you're going to have p equals to 1/8. Now, if your attributes are all binary, like what we just did, either this or that, okay, and if the probability is somewhat uniform, then every selection will come with 3 information. Do you agree? Mm-hmm. Right here, it's going to give us whether it's shiny or unshiny, or special or not special, high speed or not high speed. It's going to give you 3 information, right? So we see that while the probability is 1/8, the information content is equal to 3, right? So you have these two. What is the relationship between these two? What do you think? Can you find the 3 hidden in this number? Where is 3 hidden in this number, 1/8? Anyone? If you can find that out, you've understood why you have negative log pi in the formula for entropy.
0.275, put into a decimal.
Every information gives you,
Is it 2 to the third?
yes, 2 to the third. Right? Yeah. 8 is 2 to the third. Right? So you see what we just found out is that information content is equal to log base 2 of 1 over p. Right? You flip this upside down, and then you take log base 2. Okay. By the way, there's a, see, in computers, usually if you put log pi, this really means log base e. And there's a base change formula which says log base epi is same as log base 2 of pi divided by log base 2 of e. And this is just some number. Some number that's slightly bigger than 1. That's it. So these two things are proportional to each other. And because in most machine learning algorithms, you're either trying to minimize entropy or maximize entropy or whatever. Those are objective functions. A constant multiple doesn't play any role at all. Okay. So I think it was 1948 by Claude Shannon that this entropy was first introduced. Okay. With log base 2. So in the very beginning, log 2 was introduced because of this property. But it doesn't matter. This log could be log base 2 or log base c. It doesn't matter. Okay. All right. So once you've understood that information content is log base 2 of 1 over p, then you can change this a little bit and then move on to there. Let me just continue on to the formula for the entropy, explain what that is, and then I'll come back to this and think a little bit more about what this means, right? So another thing that you have to know is this thing called expectation value. So if x is a random variable, and let's say x could be with probability p1 a special value, so x1, and with probability p2 it could have x2, so on and so on, pn, xn. The expected value of x is really the average value of x. Okay? How do you calculate the and pi? The probabilities are like frequency. It's going to happen, right? So since this is a frequency and that's the value, taking the average really means you want to take the weighted average, which means you multiply the frequency with each value. And then divide by the sum of all the frequency, right? But if you have sum of all the probabilities, what do you get? What do you get if you add up all the probabilities?
1.
1. So it's simply summation of probability times the value. Okay? So that's called the expectation value, or the average value of this random variable. If you have this understanding, then we can now define what an entropy is. An entropy is the expectation value of the information content. So this is log of each probability. Log of p. Sorry. I forgot to say this. You know, the rule for log is like if you have division, it's a subtraction, right? What's log 2 of 1? Log of anything of 1 is 0, right?
0.
So it's gone. So this is same as this. So I'm going to put this. Okay. So this is the information content of each probability. And if you want to find the expectation value according to this formula, what's happened? It's a summation of pi times negative log pi. And once again, I don't care if there's a 2 or not. It doesn't matter. Okay? So we have this. So that's the entropy. Okay, and finally, let's give a slightly different notion of this. If probability is 1, what's the information content?
0.
0, because log 2 of 1 is 0, right? You can interpret it like this. If you know that something is going to happen, when it happens, there is no information added to your knowledge, right? Now, if something highly unlikely happened, and it happens, you've gained a lot of things, right? So, let's say my laptop disappeared, okay? Highly unlikely, right? Okay. And then immediately you have some other knowledge, right? You know that the person who took it is probably not our student, right? Probably an intruder because we're all nice, right? And that person must have gained through the front entrance, so I could look at the camera, and all kinds of information comes up from the fact that this highly unlikely thing happened, right? So when something highly unlikely thing happens, there's a huge information content that it has, right? And that's how you think about this entropy. Entropy tells you how much information content this probability distribution has. Right? Okay, that's all.